So you guys should have worked on like 1 through 40. You started on that at least. We'll start with questions from there if there are any. Mackenzie, should I set a hand?
Yeah.
Let's go.
Can you do number 38?
Yeah, sure. Okay, so 38's just like kind of a pain in the tuchus, but that's okay. All right, so I'm going to build. All right, let's just kind of draw a picture to justify what it is we're doing. So -2, 1, there's x. -8, -4, 2. It's 4, 5, 6, 7, 8. 2, 3, 4. So there's y, and then z is 5, 7. 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7 is up here. So I don't know. I think it's like this terrible looking triangle that's like almost a straight line. So what I need to do is I need the angle between, I need like this vector and this vector. So I need like yx and yz. And then I would need like this vector with this vector. So then I would need xy with xz. And then I would need like those two vectors. So I'm going to need zy and zx. So yx, head minus tail. So -2 minus a -8 is 6. And then 1 minus a -4 is 5. Then yz, so that's 5 minus -8, so that's 13. And then 7 minus a -4, that's 11. And so to find the angle between these two vectors, I'm going to use my angle between two vectors formula. So that angle is going to be cosine inverse of the dot product of these two vectors. So 6 times 13 plus 5 times 11 divided by the square root of 36 times 25, which is 61, and the square root of 13, which is 169, plus square root of 11, so 121, so that's 290, I think. So let's do that one. And I'm expecting this to be quite a small angle from the picture that I've drawn, right? Mackenzie, you doing okay? Uh-oh. Oh, what'd I forget? I forgot the 61. All right. Ha. There we go. And I'm in degree mode. Yup. So that's pretty dumb. 0.43 degrees. Okay. I was expecting it to be real small, but that's kind of bananas. All right. This next one I'm expecting to be monstrously big, but I'm just going to do the exact same thing. So head minus tail is -8 minus a -2, so that's -6. And I have -4 minus 1, so that's -5.
I guess it is 179.
Probably. XZ, so I'm going to take head, so 5 minus -2, so that's 7. And then 7 minus 1, so that's 6. So theta is going to be cosine inverse of -6 times 7 plus -5 times 6 over 36 plus 25 is still 61. And then 49 plus 36 is 85. Let's see what we get there. So 179.20.
I was right.
And I guess at this point I can find the third one by doing the triangle sum, yeah. So 180 minus this one minus, oops, this one. So 36. Drake?
Just a question. Where'd you get the square root of 290 from?
Square root of 13 squared plus 20, or 11 squared?
Oh,
Just doing the magnitude. Mackenzie, that feel okay? Some bonkers numbers, but when we actually look at the picture, it's like, okay, well, I guess that makes sense. It's basically a straight line that I had to draw there. Just the distance formula. Or you could calculate the magnitudes, right? Like the magnitude is going to be the same as the side lengths. Yeah. Which I think we have the 3 side lengths then, right? Square root 61, square root 85, and square root 290 ought to be the 3 side lengths. Because those are the magnitudes of the 3 vectors involved. So I think we have the side lengths there. Does that feel okay? Bless you. You're welcome. Amy. 32? Sure. All right, so 32 says we got 3W plus 2U dot -4V. Okay, so I'm going to do the scalar multiplications first. So W, I guess we should write that down, huh? U is 3, -8. V is -4, 5. and W is negative 2I plus 3J. So W, I'm just going to immediately translate into component form since everything else is in component form. So 3W is going to be negative 6, comma 9. 2U is going to be 6, negative 16. And then negative 4V is going to be 16, negative 20. So far, so good. And then I'm going to do the addition. So negative 6 times 6 is 0. And 9 plus negative 16 is negative 7. And then we'll do the dot product. And I just get 0 plus 140 or 140. Again, the dot product is the product of the x's plus the product of the y's. Tyler? Okay. Basically the same problem here. Okay, so the first thing I'm going to do is calculate CD. So that's going to be head minus tail, so negative 1 minus a negative 2, and then 6 minus 9, so negative 3, and then BD. So again, head minus tail, so negative 1. Minus 5 is negative 6, and then 6 minus a negative 4 is 10. So negative 5 times CB. Oh no, is that CB?
Yeah.
I wrote it down too messy, and then I read it as CD, huh? My apologies. Okay, so it should be negative 4 minus negative, so it should be negative, all right, so 5 minus negative 2, that's 7, and then negative 4 minus 9, so that's negative 13. Gee golly willikers, so negative 35, and then 65, and then that's going to be negative 6 root 2, and then 10 root 2. And we add these together. So I can't add a radical with a non-radical together, so we just got to kind of write them as an addition problem. And then I'm done. You could turn them into decimals, I guess, but the directions don't say you need to do that, so this answer would be fine. But if you want to turn those into decimals, that's okay too, I guess. I would probably not, because then I'd have to get my calculator out and punch it in. That's like 30 more seconds out of my life that I could have had to, you know, contemplate the meaning of life or something. But wouldn't be wrong to do it. Mackenzie? 24? Sure. So this is just asking us to prove the property. So we want to prove that 0.u is equal to 0. Well, I'm just going to say, okay, well, the 0 vector is the vector 0, 0. And I'm going to just say u1 is, or u is the vector u1, u2. So if I do that, the zero vector dot u, it's just going to be 0, 0 dot u1, u2, which is 0 times u1 plus 0 times u2, which is just 0 plus 0, which equals 0. And we're done. You know what I'm saying, Mac? So all I did was use the definition of what the zero vector is, coupled along with the definition of dot product, and the number 0 just fell right out of there for me. Mia, is that a hand?
Yes. Can you put 26?
26? Sure. So u plus v dot w should equal u dot w plus v dot w. Okay. So I'm just going to start by defining my vectors, u, v, and w, just kind of in that standard way. So I'm going to, as in kind of any standard algebraic proof, I'm just going to start with the left side and kind of do things until I run into the right side. So I'm going to just start by replacing these vectors with the component forms. And then I'm going to do my vector addition. Just using my definition of vector addition. And then I'm going to go ahead and use my definition of a dot product. Now everything here is a real number, so I can go ahead and use the distributive property for real numbers. So far, so good. And now I'm going to just rearrange my groups to put the things with the u's together. And then the things with the w's together. And it's okay to do this because all I'm doing here is rearranging like real numbers, right? I just have four pairs of four real numbers. I can add them in any order I want, group them together in any order I want to do that addition. That's all okay to do. Yes? Now if I look at this piece that's highlighted, that's the definition of the dot product between u and w. And this piece in green is just the definition of the dot product between v and w. So we can just write that then as u dot w plus v dot w, which is what we're supposed to be ending with anyways. Is that okay? It was a little long, but it was all like just using the definitions, right? So just to rehash what I did is I just added the vectors here to get this. I used the definition of a dot product to get to the next step. Went ahead and distributed things through. Regrouped so that I had all the u's together and all the v's together. And then used the definition of a dot product to change those products and sums of real numbers into dot products with vectors. And then that basically gets us home. This proof technique we've seen here where it's like, okay, I'm going to use some definition, convert things to real numbers. Then I can use all my properties of real number arithmetic to rearrange things however I want, turn them back into vectors, and there I'm at what I wanted. Is a real common proof technique. You guys use that in geometry a whole bunch of times to prove theorems about congruence using equivalent properties of equality, right? If you wanted to say that like, I think to do like the symmetric, reflexive, and transitive properties of congruence, you just converted them into equalities, used the property of equality to get what you needed, and then converted it back into a congruence. Like, it's real common technique to just like convert it to something we already know lots about, use the properties that we need on that in that form we know a lot about, and then turn it back after we've rearranged it to what we needed. But that's the way I would have done that. It's just as straightforward as possible. Who's next? Emma? Sure. So again, setting it up exactly the same way. I'm just going to start by defining U, kind of in our usual way. So I start with just rewriting my vectors so they're in component form. And I'm going to do my dot product. Oops. And U1 times U1 is just U1 squared. U2 times U2 is just U2 squared, which is the same thing as U1 squared plus U2 squared, like that. And I notice the piece underneath here is just my definition of the magnitude of U. And I'm done. So again, the only tricky place was doing this, where I rewrote the U1 squared plus U2 squared as the square root of U1 squared plus U2 squared squared. But that's it. Last call on homework questions. Amy? Yeah, so to show two things are orthogonal, all we need to do is show that their dot product gives us 0. So we have 8 times -3 plus negative a half times negative 48, which is negative 24 plus 24, which is 0. That's all we need. Actually, one of the easiest questions that we had. All right. So today we're going to talk some about applications of vectors. And this is, I guess it's so our first application is just going to be using vectors to kind of do these navigation problems that we had done first semester. So suppose we have a boat that leaves a port and averages 40 knots per hour, or 40 knots traveling for 2 hours on a course of 215 degrees, and then it turns to a bearing of 162 degrees and travels at 55 knots for 3 hours. What is the distance and bearing of the boat relative to its starting position at the port? So I'm just going to think about these two legs of the trip, the boat's trip, as two vectors. So my vector u has a magnitude of 40 knots for 2 hours, gives me 80 nautical miles. And the bearing is 215. So remember, bearings start from north and go clockwise. So this would be my bearing. What I want, though, is the standard position angle. So let's see, that would have been 35 in there, so that would be 55. So 180 plus 55 is 235. My other angle, my other vector has a magnitude of 165. Its bearing is 162, so it'd be like here. We want this one. So if that's 162, this little sliver has to be 18. So 270 plus 18 is 288. So now I can go ahead and add these two vectors. To do that, I'm going to resolve each vector u and v into component form. So 510 is my x component. And negative 2246 is my y component. Mackenzie? And so the magnitude for this is going to give me the distance we are away from port. So I do that, I get 222.51. Nautical miles. And then to find the direction, I'm going to go ahead and plot the point 510 and then negative 222 over. What I want is this angle. In that case, this spot is my alpha, and the x-axis part of alpha is at 360. So I can say theta is 360 minus alpha, where alpha is going to be the tan inverse of the absolute value of the y over x. So I'll just go to my calculator and type that in. So 360 minus tan inverse absolute value. I don't need to do that. This guy divided by this guy. So when I do that, I get 271.31. Or if I wanted a bearing, I guess this piece alpha is like 88.69 would have to be. Just doing some arithmetic in my head. So the bearing then would be 90 plus that, so 178.69. Depending on what the question was asking for, I don't remember anymore. I guess it wanted the bearing, so I wanted the 178.69, but if you wanted the direction, you would have said the 271.31. They're describing the same spot, but...
And you got the bearing column.
Well, this piece has to be 88.69 because 360 minus 271.31 is the 88, and the bearing goes from north, starting at due north, so 90 for the first quadrant, and then that 88.69.
Okay.
Right. So just using the same information, if I got one, I get the other. It's just a question of like converting it back and forth. And that's something that we did first semester. So even if that's like, you don't feel like a pro on that, still, it should at least feel pretty familiar. Or it's like, oh yeah, I remember doing that. That wasn't so bad. I mean, it was a little bit of a hassle, and like, I'm going to have to do a couple practice to get back up to speed on it, but should be something that we still feel like, okay, I can do that.
So the bearing would be like, if you drew another arrow down.
So this is the bearing.
Yeah, okay, gotcha. That's what I was thinking.
Yep, always from north. Okay. So the next applications, we're going to have to define a new vector operation. So like, you know how we have the vector 3, 4, and we can break that into like a horizontal component and a vertical component when we go into the linear combination form. The thing that is nice about these is that these are orthogonal vectors, right? They intersecting at a 90-degree angle. Now, are these the only vectors that would add to give me the vector 3, 4 that are orthogonal to one another? No. So what's another set of vectors that would be able to do that?
You can do 1, 2, and then you can do 2, 2.
I don't think those are orthogonal.
Oh, yeah. So you can do.
But
Does the 0 have to be in both of them?
no, in fact, it couldn't be. So let's say that we have two vectors u and v. And what we want to do is we want to break this into components. So we have like this component and this component that's in the same direction as v. Those two vectors, the red and blue, would be orthogonal vectors that would still add up to u, right?
So could you do like 0, 4, and 3?
So, well, I've drawn this particularly misleading because I drew it horizontally,
Okay.
but there's no reason v would have to be horizontal. It could be like at any angle you wanted it, and you could still do something like this, right? So this blue vector, we give the name, we call it the projection of u onto v. And basically what that vector is representing is the portion of u that is in the same direction as v. Now, this is something that becomes really practical in a real world sense, particularly in a physics situation. If you have two things interacting with each other at an angle, you can figure out how much of one thing is acting in the same direction as the other thing. Becomes particularly a useful thing to create. So this other thing I'm going to just call, this other side I'm just going to call W. I don't know why I wouldn't write it in red though, considering we're talking about the red. So what we can observe here is that W plus the projection of of u onto v is just going to give me the vector u back. I know that because I've drawn these two things head to tail. That's just the definition of vector addition. Or you could say that that vector w is equal to the vector u minus the projection of u onto v. Those are equivalent statements, right? All I did was subtract the projection from both sides to get this from the first one to get the second one. So the big question left is like, okay, how would I calculate this projection then? Well, we have a formula for that. So given non-zero vectors u and v, the projection of u onto v is equal to u dot v divided by the magnitude of v squared times the vector v. So that's our definition for how we calculate a projection of one vector onto another. So a couple of things to look at here. Notice in the original drawing here, when I drew my vector v, I kind of drew that arbitrarily long. In a lot of senses, the length of vector v isn't really that important. I'll call these finer points here. So it's often not important, that length of vector v. So we can assume that the magnitude of v is 1 in many cases. What really is important to us is the direction for v. Because if we look at this portion here, the dot product of u and v divided by the magnitude of v squared, the dot product of u and v is just a real number, and the magnitude of a vector is just a real number. So really, what is this projection? It's just a scalar multiplication, right? It's essentially scaling vector v so that it represents the component of u that's still in the same direction as v. So let's do a couple of examples here. So we'll start with just a numeric one. So it says, find the projection of vector u onto vector v, then express vector u as the sum of two orthogonal vectors, one of which is the projection of v onto u. So there's really two parts of this. We'll start with the first part here, just finding the projection of vector u onto v. So if I wanted to do this, let's just kind of sketch a picture here in the beginning. Now, it's not necessary really that you're drawing a picture of these things. But, you know, as you're kind of getting used to doing these things, I think the picture can be helpful. So I plotted something that looks like, to me, 3, 1, and then 6, negative 4. So what we're looking for then is this guy's my W, and this piece is the projection of U onto V. Everybody okay with the picture that I've drawn here? Again, I think it helps develop a little bit of intuition, although not necessary. Oops, squared. So we'll just start with our formula. So u dot v is just the product of the x components plus the product of the y components. And the magnitude of v squared, well, that's just going to be 6 squared plus negative 4 squared. square rooted and then squared. I'm not going to bother with the square rooted and squared though, because they're just canceling each other out. And that's all going to be multiplying to my vector v. So that's 18 minus 4, so 14. And that's 36 plus 16, so that's 52. Oops. And really, let's reduce that, right? Probably makes more sense to call that 7 over 26. And then if I do my scalar multiplication there, then, and I'm just for the record, I'm going to be reducing as I go. So there's my projection of u onto v. Again, I reduced as I went. You could not reduce and wait all the way to the end to do your reducing or whatever, but at some point you should reduce your fractions. I'm good at mental math, so I just kind of reduced in my head as I went. You're free to reduce later at the end or however you feel most comfortable though. Does everybody feel okay on that? Okay. Then the question asks to express vector u as the sum of two orthogonal vectors, one of which is the projection. So we remember that the projection of v onto u plus that vector w should give us vector u. So I know immediately that w should be the vector u minus the projection of v onto u. So u was the vector 3, 1, and the projection of u onto v was what we just found, 21 over 13, negative 14 over 13. So let's see, 3 is 39 over 13, so 21 minus 30, or 39 minus 21 is 18. And then 1 is 13 over 13, so minus a negative 14 is going to be 27 over 13. So that's my vector w. And from that I can say then my vector u is equal to my projection of u onto v plus this vector w and those two vectors I know are orthogonal because of the definition of a projection. And you could check that if you wanted to by adding the two vectors together and make sure you get 3, 1, which you do. And you could do the dot product of those two vectors and make sure that they give you 0 to show they're orthogonal, and they will. So far, so good. Again, I know this is new and can be kind of challenging. I'm trying to go not too fast so that we're doing this kind of carefully. Let's do another example. This time it'll be a story problem. So here it says Kyle is going sledding on a hill with a 25-degree angle of incline. If Kyle and the sled weigh a total of 65 pounds, what amount of force is sliding down the hill? So those of you that are in a physics class, this should sound like a familiar physics scenario and something that you're certainly interested in. So our little setup here is going to be to draw a picture. So I'm going to start with my hill vector. So this will be my hill vector. And I know if the angle of incline is 25 degrees, that also means that this angle here is 25 degrees. So the direction for my hill vector is 25 degrees. Everybody cool with that? So that's one vector. That's the vector I'm going to be projecting onto because we're asked to find the amount of force sliding down the hill. So we're going to be projecting one vector onto the hill. For my other vector, it's this weight of 165. So my physicists in the room, just any object that has a weight associated with it has a force associated with it. That force is due to what? Gravity. And what direction is gravity pulling?
Down.
Straight down. So I'll call this, let's call it G for gravity. That makes more sense. And so what are we doing then? There's my vector W. So this guy right here would be my projection of gravity onto the hill. So I'm going to start then by resolving my two vectors, G and H, into component form. So for the hill vector, are we told anywhere in the problem how long the hill is?
No.
No. So what can we assume about the hill? I'm just going to assume its magnitude is 1.
Okay.
So if I do that, I can resolve this into component form by doing magnitude times cosine of the direction, and then magnitude times sine of the direction. So 906 and 423. Okay. So now for our vector G, the direction for G is 270. And the magnitude of G is 165. So 165 cosine 270, 165 sine 270, which not surprisingly comes out to just 0, negative 165. You probably were thinking from the picture I drew, Mr. Kulak, no doy, that vector is going to be 0, negative 17, or 165. Since the length of that vector is 165 and it's pointing straight down. And I'd say, sure, I like to do it this way just so you can see that the formulas that we're using, but there's nothing wrong with just looking at the picture and going, oh yeah, that certainly has to be 0, negative 165. No biggie. Everybody feel okay so far? Okay. So the projection of G onto H is going to be H dot G divided by the magnitude of H squared times H. So just plugging those parts in, I have this. Everybody okay with that? So that gives me negative 169.73. I'm sorry, positive 69.70, or negative, jeepers creepers, try it again, Kulik. Negative 169.73. And then I just need to multiply that piece in to each one of those. So that gives me 73.20, or negative 63.20, and then negative 29.20. 29.47, excuse me. Oh my goodness. Yeah, well. Stop here for a moment. Did Mr. Kulik do something dumb?
I hope not.
What's really the direction here?
Oh. Right. It's like
325.
25. Yeah, not 25.
Yeah.
It's funny.
335, excuse me. I did it again. Don't worry, it doesn't change much. So that should be a negative sign. That should be a negative sign. That's going to be a positive. So that's negative still. That's positive, but that's negative. So just lost some signs when all flipping around on us. Little flippy floppies. My apologies. Checks. Yes. Okay, so that's the vector that's going in the same direction as the hill. What we want, if we want the force then, going down the hill is to just take the magnitude of that vector. And I'm going to just use, I realize that the numbers that I'm using aren't the right signs, but it doesn't really matter since I'm squaring them anyways. So I acknowledge that I'm using the wrong numbers for my calculator, but it doesn't really matter. So 69.73 pounds in the direction, or we'll just say down the hill.
What is that? Plus what? Oh, that's fancy.
Hmm. 6973. Did we run into that number earlier?
We did.
What was that 6973? That was just the dot product of our vectors g and h, right? Well, Mr. Kulik, I'm curious. Is that always the case? Is like the magnitude of this projection just equal to the dot product? Well, maybe this time it was. Or maybe whenever this vector v that we're projecting onto is a unit vector, the magnitude of the projection of u onto v is going to equal u dot v. Let's see if we can prove that. This is potentially quite useful as it saves us a lot of time on some of these problems, right? Let's see. So we'll start by doing our formula for the projection of u onto v. Oops, squared. And I know since v is a unit vector, what's the magnitude of v have to be? If v is a unit vector, what does the magnitude of v have to be? 1, right? That's the definition of a unit vector. And u dot v is just a scalar, right? And we talked about how we can pull a scalar out of a magnitude. That's okay. And the magnitude of v, again, is equal to 1, since v is a unit vector. And there we go. So if you're projecting onto a unit vector, the magnitude of that projection is just equal to the dot product of the two vectors. So on that previous problem, we could have stopped and just calculated the dot product of the two vectors and not had to go through all that hooey. That's pretty rad. Now, is that always going to be the case?
Unfortunately, no.
No, unfortunately, no is correct. Let's look at another example where that shortcut doesn't exist. Oh my goodness. All right, so here we have a crate, being pulled up a ramp at an angle of elevation of 40 degrees with a force of 100 pounds. The ramp measures 10 feet horizontally and 2 feet vertically. Assuming the crate is of negligible weight, what is the amount of force directed up the ramp? Well, I'm going to, again, draw a picture here. So here's my crate vector that has a magnitude of 100, and the direction of that crate vector is 40 degrees. I don't have to adjust that, notice, because we're in the first quadrant. Everybody's okay there? And then I have my ramp vector, so that's 10 feet horizontally and 2 feet up. So maybe that's my ramp vector. Everybody feel okay with the picture I've drawn? And what I'm going to be doing then is projecting that crate down onto the ramp. Okay. So we'll start by rewriting the crate vector in component form, doing the same thing that we did before. And then we need to rewrite the ramp vector in component form. Mr. Kulik, I don't know the magnitude or direction of the ramp vector. You know something better than that, though. You know its component form, since it's 10 feet horizontal and 2 feet vertical. The ramp vector is just, component form is 10 too. Dang is right. Now observation. What's the length of R? It ain't 1, correct? You can tell right away because the square root of a squared plus b squared is not 1. Everybody's good with that? So we know that we can't do the shortcut that we had just talked about here. So the projection of C onto R is C dot R divided by the magnitude of R squared times vector R. So C dot R is 10 times 100 cosine 40 plus 2 times 100 sine 40 divided by 100 squared plus 2 squared, all times that vector 10 to.
Wait, what's in the bottom?
100 squared plus 2 squared?
Under C plus, times R.
The magnitude of R squared? The vertical bars around R?
Between.
Huh? What? You're asking about this, right?
Yeah, what is that?
That's the magnitude of R squared. Yeah, that's what I said.
Sorry.
That's okay. That's okay. It's okay, man. It's okay. All right. So let's do it this way. I don't feel like typing this in a trillion times, so I'm just going to do it, you know. Everybody's okay with what I'm doing here setup-wise? And then to get the first component, I multiply that by 10. So 849. Oops. That's not the right numbers, though. That is right. Cosine 40 What is going? Why is this not giving me the right value? All right. Ten times 100 cosine 40. Okay. And then plus 2 times 100 times sine 40. Okay, that seems good. Over 100 squared plus 2 squared. Okay. Great googly moogly, what's going on here? This is not working out the way it's supposed to. There we go. Divide by 104. Okay. There we go. I don't know why it was given. I don't know. I don't understand my order of operations problem on the previous one, but there we go. 8602. That's better. And then 1720. I don't know what was up with that. So that's my projection vector. But what I really care about is the magnitude of that vector. So 8772 pounds up the ramp. Oh! One thing with the shortcut. Haha, I forgot this. So we said this, right? And not necessarily true. Here's the one little revision that we would need to make here. When I take the magnitude of something, I'm always getting what kind of a number? Non-negative, right?
Yes, I agree.
The dot product, can that be negative?
No.
Yes.
Oh, okay.
So really we need like an absolute value symbol around this.
Gotcha.
But that's okay because when I pull the dot product out of the magnitude, again, that gets an absolute value around it. So everything is fine. And then that turn your frown upside down.
We're actually good.
Yeah. So you guys should be able to do 41 through 50 at this point. So let's add that into the problem set.
Sure.